Okay, welcome to the introduction to finite state machines. We're going to understand states and transitions in interactive systems. We're going to learn about the finite state machines, what states, transitions, and entry-exit actions are. We'll talk about real-world examples, why finite state machines are useful for the design of various systems. So what is it all about? It's an abstract model. That means that it's a set of ideas that represent a real system or set of things, but states themselves are just an abstract concept. Okay, so they describe a system that can be in one or more of a fixed number of states. That's where we get finite from. And it can change from one state to another in response to events or conditions or inputs, etc. So some examples would be how a video game character that can be idle, walking, or jumping can be planned as a system. The turnstile in the real world that prevents you from entering or exiting in the wrong direction without having paid. Or a vending machine as an interactive system. In fact, in the turnstile system, we can describe it as two states, right? Locked and unlocked. This black dot represents the pseudo-state of beginning, so we always have an entry point into our finite state machine. We're beginning here into the locked state, and then what two things can happen? Well, we can have a push from a user, and that will transition us back to the locked state because we expect that nothing is going to happen there. And then alternatively, they can pay, and in this example, it's a coin, and that should transition it to a different state, an unlocked state. The coin should open the lock and allow the user to push and open it. Then if it's unlocked and a user puts a coin in, nothing should happen also. I guess we just get free money, so the transition goes back still to the unlocked state. Then the unlocked state needs to return to the locked state, so if the user pushes the turnstile, then that push action should also return the system to a state of being locked. So let's look at that simple example with something else called a state transition table for the turnstile. So we knew that it had two states, locked and unlocked, and the two kinds of input that it can get were the payment, the coin, or the push. And then based on the state and the input, what it will be the next state. So first, the locked state will go from the locked state with a coin input to the state of being unlocked. And we can describe the output, unlock the turnstile. Okay, easy enough. So the locked state, if we push it, it remains locked, so it transitions to itself, and there's no output. And the unlocked state is the same function. In the unlocked state, when we pay the coin, we stay in the unlocked state, and there's no real output in this simplified example. And if we're in the unlocked state and we push, the next state should return us to the locked state when the customer has pushed through. In a real turnstile, we expect that there are other states. There might be an error state or a more complicated state where the user pays when it's in the unlocked position. What happens then? But in this simple example, that is a complete finite state machine. So some key components of a finite state machine. Obviously the state. So the different modes or situations the system can be in. So here we might start with something called a passive state. So this is the title of the state. Here we call an active state. We can call these anything we want. The transitions are the arrows between states. They have rules and triggers that move the system from one state to another. And they also have events and inputs. So what causes the transition, like a button press or a signal or a timer. Those triggers and events and inputs are all written by the arrow. Okay? And the actions, too, are all written by the arrow. So what happens when you enter or exit a state or during a transition, that is written by the arrow. Now, there's one exception to this rule, and that is when you enter a state, something might happen, and when you exit a state, something might happen, and you write that right in the state. So let's look a little bit more about what the states mean specifically. So a state is a specific condition or situation in which the system waits for something to happen. It could be waiting for time. It could be waiting for the result of something. It could wait for input. So in vending machine, idle is a state because it's waiting for a user to come and interact with it. Coin inserted or payment inserted is another state. Dispensing the item and an error state like out of service are all potential states for a vending machine. In the elevator example, Moving up, moving down, doors opening, doors closing are all potential states. We could describe the elevator with different types of states as well. Moving up and moving down could be substates under the idea that it is in the state of moving. So how you approach this may be different. There are different ways to approach a finite state machine. There's not always one right answer because we're describing something abstractly. Think of a common household application, household appliance, like a microwave, a blender, and list the possible states that it could be in. Okay, so the initial state of a machine, that's that black circle there, that's that initial state. We call that a pseudo state because it's not really a state that it's in. This is indicated here, it's a transition into the first state, okay? Similarly, the final state is a black circle with another circle around it. Okay, this is the end state. It's also a termination. So some state machines will never terminate. They will always return back to an initial state, or all routes through the state machine will eventually become a continuous loop or a closed loop. So in an open loop finite state machine, there is a final pseudo state. Okay, so the transitions bring us from one state to another state. In the initial pseudo state, we begin and we transition into the first state. Typically, that's when the system starts, is powered on, is activated, is run, is reset, whatever that looks like for that system. A transition is the movement from one state to another, and it's usually triggered by some kind of event or input. So a user event or input from a sensor or a timer. So the vending machine gets payment, so it moves from idle to payment received, or in this case, the coin. The elevator reaches a desired floor, so it moves from moving up to opening the doors. These are the transitions. Okay, let's look at an abstract example of a finite state machine. On the right, we've got S1, S2, S3, and S4. These are the potential states in our system. Then we have transitions here. We have some transitions that go from one state to another. We have transitions also that loop back into each other. That is the self-transition here in S2. Let's process these regular expressions and see if we can get to the desired end state, the S4 state here. Okay? So it's asking us, which of these strings cannot be processed by this machine? Let's see. We have ABA, CD, AA, C. So this regular expression is a way to abstractly move through the transitions and states of a finite state machine. Let's try it with the first one. Starting in S1, ABA, so A brings us to S2, B, A, so we're at S2 again, C, D, A, and C. So the first one is correct. The second one, A, B, A, C, well, we'll go from S1 to A, back over through B, through A, and then over to C. So the second one is also correct. The third one has 6 A's and a C, so we start in S1, then we go through A, and then we self-transition through A into state 2. So state 2 cannot be left using A, and then C. And we end up in state 4 again. The last one, 4, is really the same circumstance. So starting with state 1, going through A, self-transitioning through A, going through C, and then ending in state 3. So the fourth one is not processed by this machine because we don't end in the desired state. Let's look at a video game example. Here we're describing the states that a character can be in a video game. So this character can stand as a state, run as a state, and jump as a state. And then we expect input from the user. Here we expect button pressing like up and A and nothing being pressed. The transitions represent the movement from the standing state, and the standing will have a certain set of actions and things that can happen to the character, and then A is pressed. And then when the character is in the jumping state, a different set of animations and characteristics happen for that character. And if you press A while you're jumping, well, let's suppose you can just jump again, so we self-transition back to the jump state. If we go from jumping and we press the up button, we go over to running here, and then we can jump again. From jump, we can press nothing, and then when jump is completed, we can go back to standing. If we're standing, we can press nothing and stay standing. So this is a way to describe how inputs at different times and different states of a character will behave. Let's look at also the special case of entry and exit actions. So when we move into a state or move out of a state, we may want to perform certain actions, okay? So an entry action for dispensing item in the vending machine would activate the mechanism to drop the product. Every time the state starts, and if the state is dispensing item, then that action should take place. Then the exit action for dispensing item might be stop the mechanism or reset the counter. So this is a shortcut for the diagram, because we could write this as a transition. But what must be true is every time we enter this state or exit the state, we want this action no matter what. So if it's conditional or if it's based on something else, then it must be in the transition arrow instead of written in the state. So the anatomy of a finite state machine for our course is going to look roughly like this. We're going to use the initial pseudostate symbol to start our diagram. And if it is an open loop system, then we're going to have a closing state as well. Our states are going to be defined by rounded rectangles. And we'll have transitions as simple arrows. We'll have entry and exit actions in those states. We'll name the states. And for each transition, we're going to say what triggered the transition, what might need to be true in order for that trigger to actually happen, and what is going to happen. So the trigger, guard, and action system is going to define how, why, and when we transition from one state to another state in a system. We're going to have self-transitions here, where we might not be leaving a state, but a trigger will be activated, perhaps a timer to initiate an action, and that will be a self-transition. Sometimes we need to make a decision based on a state and a set of triggers or actions. This rhombus, or this diamond here, is going to allow us to branch from one state to multiple optional states depending on what the condition is here. In this example, the state of selecting a message format in software was provided. And then if the message format was to be voice, we would go into a different state than if it was SMS or, wow, fax. Finally, another special case might be concurrent states. We might actually want to have two states. We might want our system to exist in two states at the same time. And in order to express this, we create what's called a region. And this region is represented by a larger state, which is just the rounded rectangle. And we're going to use this black bar here to demonstrate that we're splitting and moving into concurrent states. And this dashed line shows us that these two states exist at the same time. In this example, the applying brakes region is describing both the front and rear substates happening at the same time. Okay, finally, tips for designing a finite state machine or describing a system with this methodology. First, you want to look at what are the different states that the system can have and list them. You might go back and change that and tweak that abstract thinking, but describe in what states can this thing do or be, what type of input or triggers will cause changes in the system, how will it go from one state to another, Is it automatic? Is it timed? Are there sensors? Is the user involved? And finally, what actions or things does the system do? What is happening between those state transitions? And what is happening once the state starts? And what is happening when the state ends? Okay, that's it for now. We're probably going to move into some